All right. It's it's time to finish up the problems. I lied, man. I was way more ambitious when I wrote the problems. I think I have like 3 pages, maybe 4 left. So I'm going to try to do as fast as I can. Number 6 here on my practice sheet says calculate the solute potential. And I've given the 0.3 molar sucrose solution at 20 Celsius. All right, so I went ahead and wrote down the equation in advance. Sucrose does not ionize, so the I value is going to be just 1, so it doesn't change anything because sucrose does not split into multiple particles. A reminder on here, you can use any R value you want. It's based on whatever pressure units you're using in the problem, but here they are. So if it's in kilopascals, you would use 8.314. If it's in megapascals, you'd use 0.008314. Bars is the one we're going to use because 1 bar is approximately 1 atmosphere. Temperature is going to be in kelvins, so remember to add 273 to your degrees Celsius value. And the concentration is measuring molarity, which is moles in solute per liters of solution. All right, so back to the problem here. 0.3 molar, 20 Celsius. We got to figure out what's going on here. I can't pause it, Charlotte. What do you need? Here's Charlotte. She came to give me a hug. All right. So I worked out the problem here. Oh, cheated and showed you the answer. So water or solute potential is -1. That's our value for the C. That's our value for I. I can't write because I'm writing I'm trying to write while looking at the screen. All right. I times C times R times T. Oh, there we go. So -1 times 0.3 molar, that's moles per liter, times 0.08314, that's liters times bars over moles times kelvins. The units probably don't matter a lot to you, but I'd like showing why they cancel. Times 293 Kelvin. Remember, that's 20 Celsius plus 273 to get to Kelvin. All right, so let's take an estimate first. So the 1 doesn't matter. I can leave that off. I've got 293 here. That's basically 300. And this number here is basically 0.1. So 300 times 0.1, what's 1/10 of 300? That'd be 30. And then 0.3, that's roughly a third. So 1/3 of 30, I'm going to say my answer should be about 10. And my units for all of these answers for water potential are going to be either units of bars or whatever different units you're using for pressure. Put this in the calculator. And after the magical number box came across, we got -7.3. Oh, shoot, I forgot the negative, Freeman. Yeah, it's a problem. They're all going to be negative. -7.3 bar. And that, remember, that's a unit of pressure. It is pressure pushing the water. And the more negative your pressure is, because you think high pressure would be pushing the water out, negative would be allowing the water to come in. That's negative pressure. All right, so the more negative it is, the more likely it is for water to come in or move toward that side. Oh, that wasn't too bad because I worked out the problem in advance. I cheated. All right, so we'll get on to some other ones. Number 7, where is the greater free energy if we've got a cell with concentration 2 molar versus a 2.5 molar solution? This is higher concentration, lower concentration. And we said that the highest solute potential, which is like potential energy, would be distilled water, which would be 0 bar. Okay, so if the highest is going to be 0 bar, which one is greater out of these two? Well, this one is. The 2 molar, because it's closer to 0. It's closer to having less stuff in it. It is closer to being in an ordered state of emptiness. B, what type of a solution is this? Okay, so we've got a cell with 2 molar. Put in a solution of 2.5 molar. Aha. Okay, so where's the water going to go here? We've got a lot of particles on the outside and not very many on the inside. That's a little bit of an exaggeration. So the water is going to be going out. Remember, it's going to go from greater free energy, higher potential energy, to lower potential energy. So the water is going to go out. What type of solution is this when the water goes out? Well, it's going to give us a skinny cell in the end. Is that going to be a hypo or a hyper? I think it's going to be hypertonic. All right. What will the direction of water movement be? Shoot, I already answered that in part B. Out of the cell. And why can't the solute diffuse freely? Why can't these particles come to the inside? Semi-permeable membranes. And what is a semi-permeable membrane made of? It's made of you guessed it, phospholipid bilayer. Won't let the particles across it because they're either too charged and they've got a shell of hydration around them, a shell of water molecules stuck around them, or they're just plain too big to get across. That was not bad. All right, number 8, we're getting into the meat and potatoes. Cell is at equilibrium with its surroundings at 25 Celsius. Oh, shoot, we're going to get out the equation. We know that we've got 0.4 molar inside the cell, 0.2 molar outside the cell. So water's going to be going where? It's going to be going from the high potential energy is low concentration. It's weird. So water's going to be going from the outside to the inside. I'll make a note of my H2O movement. All right. How is it possible for this to be at equilibrium if they aren't at the same concentration? Well, that is easy. Because, where's my equation sheet? Because the total water potential is the solute potential plus pressure potential. So pressure must be playing a role. Plus solute potential equals the total water potential. Ha ha! I should probably call that pressure potential. All right. So, I think that's a fine answer right there. And is this possible for there to be pressure on the inside of the cell? Yeah, because water has been moving inside the cell because it's going from a lower concentration to a higher concentration. So the water is trying to dilute this down. All right. B, solve for the water potential of the solution. Okay. That's going to be outside the cell. So equals negative, got to remember the negative, I times C times R times T. All right, and it's solution. So we're talking about outside the cell. And, oh, idiot, you didn't even tell what type of thing it was. Let's make it salt. All right. So it is salt. That means our I value is going to be 2 because sodium and chlorine. So negative 2 times outside the cell is 0.2 molar times 0.0831. I'm not going to worry about my units because I'm running out of space. Times the temperature. It's at 25 Celsius. 25 plus 273 is going to be 298. Kelvin. All right, so again, I've got 300 times about 0.1, so it's going to be about 30, times 0.2, which is 1/5. So 1/5 of 30 would be about 6, times 2, and it's negative. So 6 times negative 2, I'm going to estimate on here about negative 12. And my calculator's on my phone. This is kind of embarrassing. Negative 12 bar. Oh, grab my other machine. All right, let's check this out in the magic number box. So, negative 2 times 0.2 times 0.0831 times 298. See how good my estimation skills. Negative 9.9. I think that's close enough to 12 to call it good. All right, so negative 9.9 bar. Beautiful. All right. Find the water potential of the cell. Oh, of course. All right, so I've got to do the exact same thing again. The only thing that's going to be different in here is this this concentration, because we still got our R values the same. The temperature is the same. We're still dealing with salt. So all we would have to do here is replace the 0.2 with a